Today we'll be talking about special senses. These include smell, taste, sight, and equilibrium. First, smell. Olfaction is the word that we use for our sense of smell. You've already learned about the olfactory nerve. That's the nerve that goes to your nasal cavity and allows you to bring in these scents and smells. So olfaction is the detection of odorants, that is, molecules that are volatile or airborne. Now these molecules, they're chemicals. They have their own unique combinations, and those create all the different smells that we have. So coffee has its own chemical combination, makes that molecule. We interpret that as smelling like coffee. Same thing with something disgusting or stinky. That's that combination of chemicals setting off our receptors in a specific pattern that our brain interprets as it smells bad. Now, your olfactory epithelium is a sensory receptor organ in the top of your nasal cavity, and it is going to be lined with chemoreceptors. They're receptors for chemicals. Here we can see all the parts of the olfactory system. The olfactory tract, the narrow part of that cranial nerve. It comes to the enlargement that we call the olfactory bulb. From the bulb, a lot of small olfactory nerves come down into the nasal cavity, located in the olfactory epithelium. Now right at the edge here, we're going to see that their small chemoreceptors are located on the end, and when those odorants come up into the nose, they bind to all of those chemoreceptors, and the way that they get activated and bound, that is going to tell the brain how to interpret. Olfactory stimulation is shown here as we start with an odor in our external environment. It comes up into our nasal cavity as we breathe or we sniff it up. The olfactory nerves are bound to those molecules, become activated. They carry that message up into the olfactory bulb, which then travels on that tract back to the brain. Here's a closer view of those receptors. We're going to start at the top with the olfactory bulb. In the olfactory bulb, we have nerves that come down in synapse with our olfactory nerves. These are going to travel down through the bone, called the cribriform plate, down into the olfactory epithelium. Here we see the cell body of one. Now these nerve cells will have a short dendrite process that ends right here past the olfactory epithelium. Tiny little cilia projections called olfactory hairs are going to come off of the very end, and they are going to house the chemoreceptors. Now all of this is in the protected mucus layer. We have many different types of scent receptors, at least 400. Now, in different combinations, we're going to see these molecules come into the nose, and we have 1, 2, and 4 get activated. That is going to be interpreted by the brain as a specific odor. We can detect over 10,000. So it has a specific combination of chemicals for the smell of orange. Has a specific combination of chemicals for the smell of stinky socks or armpits. That's not a good combination. But flowers as well. Let's look at a table of different odorants and see what's so different about these chemicals that our brain is interpreting them as all these different odors. On this table, on the left, we have the name of the compound, so methyl acetate. Now that gives us a sweet fragrance, or nail polish. Not sure how those are together. And here is the chemical structure that gives us this smell. Now, an apple or a pineapple has a compound that looks like this. It's called methyl butyrate. This is a fruity smell. Wine has ethyl acetate. Banana, we're going to see that. A pear, an apple. So those are all very similar. So let's look at a non-fruity. Here's some of those different aromas that you recognize very quickly. Cinnamon, vanilla, anise, thyme. And here's a lot of those smells you would rather not smell. Fishy ammonia, rotting flesh, and feces and feces. Somehow, feces and flowery go together. So all of these different chemicals are going to be called the odorants. Next up is our sense of taste, called gustation. We're able to taste whenever we chew and bring things into our mouth, mix it with our saliva, pound it until it's a little smaller and we're getting those individual molecules. Then we bring them into contact with special cells called gustatory cells. These cells have tiny chemoreceptors that are going to detect taste sense in the food, small dissolved molecules that stimulate our gustatory receptors. If you look at someone's tongue, or your own in the mirror, you are going to see a lot of small bumps covering the surface of your tongue. These are called papilla. Our taste buds are going to be clusters of those gustatory cells that are embedded in the crevices surrounding your papilla. There are 4 different types, and we see that some of them don't even have taste buds, and some have the vast majority. This slide shows us a tongue with all of the different papilla pointed out. We have filiform papilla, located mostly on this surface of our tongue. It gives us a roughened texture. Whenever a cat licks you and it actually hurts, that is because they have much larger, more keratinized filiform papilla than us. Ours is a smaller version, but it gives that same roughened feel to the top of the tongue. These have no taste buds. Next up are the fungiform papilla. The fungiform are rounded and they have very small taste buds, but they're mostly on that tip of the tongue. The foliate papilla are located on the sides of the tongue. Now these do have taste buds, but they have the majority of them in early childhood, and as you age, a lot of these are going to die off. Maybe that's why as a child, they seem to be very sensitive to different tastes that we as adults don't seem to mind very much. Lastly, we have the valate papilla. This is your least numerous type of papilla, but it has over half of your taste buds. We see them in a row on the very back posterior side of the tongue. There's about 8 to 12 of these on average. And here we're going to have our taste buds on average. And here we're going to see all of our taste buds located in the crevices around that papilla. Here's a closer view of one of the taste buds on the side of that papilla. When you first see a taste bud, its appearance is kind of like that of an onion. There's the side that has the sensory neuron coming into the back of the taste bud. Here it will attach to the different gustatory cells, shown here in light pink, which are sandwiched in between all of these supporting cells, done in orange. Your gustatory cells at the very end have gustatory microvilli. It's here that we have those small chemical receptors that are taking in the taste sense dissolved in the saliva, interpreting the signals that they receive, and sending that in through the sensory neuron back to the brain. All of that sensory input from your taste buds comes into your brain through one of 2 pathways. For the valate papilla on the posterior side of the tongue, also that lingual area, you're going to see cranial nerve 9. The rest of the tongue is going to be supplied by cranial nerve 7. What we interpret as the different tastes of our food are going to be based on if it contains sugars, then we detect that as sweet. If it contains salt, it's salty. Acids has a sour taste. If it has alkaloids, it has a bitter taste. And if it's like a burger and cheese and it's just that's going to be the amino acids, and that's called umami. So ice cream would be sweet. Fries covered in salt would count as salty. For sour, think of something like vinegar. And for bitter, think of dark chocolate. Then we have that hamburger and fries from umami. When you go to a Mexican restaurant and they want to put that cilantro sauce on your food, are you repulsed by that, or do you think it's delicious? The reason why you say either yes or no actually depends on if you have a mutation that allows you to better detect the aldehyde in cilantro. Aldehyde is a type of fat molecule that we're also going to see in fragrances, essential oils, some insect body fluids, and you might detect that and think of it as gross. So how well you detect that molecule can actually decide how your brain interprets the taste of cilantro. All right, taste is done.